So as we saw in the previous slide, the Cortex-M3 general-purpose registers are used as a container for different instruction operands. However, this is not the only functionality about or of those registers. This register can be used as a container for different input parameter of a function call, as well as container of the return value of a function call, as a container of the local variable within the function body definition, and many aspects related to your program execution flow. The functionalities of those registers are linked to the Cortex-M3 calling convention, and to have better understanding of this Cortex-M3 calling convention, we need to have a good understanding of the C-level calling convention. But briefly, to give you an example, if you are defining a function that has some input parameters, a return value, and some local variables, then this calling convention is creating this link between this C-level parameters and assembly level parameters. For instance, the first parameter of a function call within the Cortex-M3 will be saved within the register R0. The second argument will be saved within the register R1, and so on. This table gives a short description about the calling convention within the Cortex-M3. R0, R1, R2, R3, those registers are called scratch registers, and use it mainly to save and hold the value of the different argument of a function call. R0 has double functionalities. Besides holding the first argument of a function call, it can be used as well as a container for the return value of a function. As this value is saved within the internal CPU register, then the CPU can access fastly on quick manner basically this value without the need to go to some external memory to get these values. This minimizes, of course, the latency to get this value and speed up the execution flow. The same concept applies for the registers R4, R5, R6, R7, R8, but those ones are not used basically to save or contain the argument of a function call. They are used to contain and hold the value of local variables within the function body. Same thing, as those variables we are saved within those registers, then accessing those variables will be quite fast from CPU perspective than accessing them and getting them from external memory. Those registers are called Kali saved, and those scratch registers are called color saved. The main difference is that it's up to the color to save the value or the content of those registers before jumping to another function. Here, it is the other way around. So it is the responsibility of the function or Kali that has been called to save and maintain the value of those registers. R9 can be used as well as a container to store and save basically the local variable value, but also it has some other functionalities. First, it can be used as thread pointer base address. For within a multi-threaded system, each thread will have kind of context, and each context will be located in some area of the memory, so it will have a different address space. If we are going to switch from one thread to another, then we need actually to back up and restore the address of each context or thread context. R9 is used actually to hold the address of each context. So if you are going to switch between, let's say, thread T0 to thread T1, then we are going to back up, so T1, then we are going to back up basically the address of the context within the R9 related to a T0 within the memory. Then we need to restore and get basically the address of the context of T1 to R9 before jumping to T1, and then the thread number 1 will get basically his context out of the address located in R9. R9 can be used as well as a base address of the lookup table used within the procedure and dependent call. In general, if you are linking statically basically your program, then the address of your function or the address basically of your data are fixed, either within the address of flash, RAM, and so on. If, for instance, we are dynamically linking the program like we do for a shared library, then the addresses of the function and the address of the data must be kind of flexible and will be independent. It means can be located in flash, can be located in RAM, can be located in some external memory, and so on. Therefore, to access this data and function, we need to go through some kind of lookup table where each index of this table will contain basically this independent address of that data or the independent address of that function, and so on. and the base address of this lookup table will be actually saved within R9. So your program will need to first access R9 to get this base address of the lookup table, then access that lookup table to get the address of certain variables and functions. R10 and R11 are used as well as a container for different local variables of a function call. R12 can be used as well as a container for local variable definition, but has also some double functionalities. Means it can be used as intra-procedure call registers, and can be used as well as a way from the linker to answer some kind of winner. To explain this, if we are branching to one function, and we are using branch with link, we need to know that this branch with link can only jump to certain address. This range will be plus minus 32 megabytes. So if we are having a function located outside of this range, then we will face some issues. And to solve this, we need to insert kind of jump table or kind of winner to jump first to a location within this address range, and this one actually will jump then to this function. And this is how actually we solve this kind of problem. This means that within this extra point that the linker will insert, we need to load basically the address of the function that we want to jump to some register, and then we invoke again a branch with link. So if we are doing a branch with link to a function F0, then the link that is outside the range of the 32 megabyte, then the linker what is doing is going to insert some kind of winner point here. So in assembly level, we'll have actually in reality this kind of winner, then F0. So it's totally new function, and then this winner actually will load basically the address of the real function to the register R12, and then we do another. So this will have the address of our main function F0, and then we are doing a branch with link to R12. Sorry, F0 here, and then we are branching basically to R12. This we can see actually for big-sized program, or if you are having some function located on ROM and then you have your main program basically within Flash or within RAM, quite far basically from those functions, then we can see that the compiler will insert basically this intermediate point to enable this kind of long jump. Finally, of course, we have those three registers that we have discussed in previous slides that maintain the execution flow of your program. So R13, which is referred as well to the stack pointer, is pointing always to the top of the free memory or free space of the stack area. We have as well the link register. It holds basically the return address after a function call. And finally, we have the program counter, which holds the address of the instruction to be executed.